All right, here we go as quickly as I can. So I remember last year I had students who, well, I did the integral stuff, and they were kind of getting it, but they were still kind of slightly confused. And when I went into this explanation, which I did not record last year, it seemed to click a lot more with a lot of students. So what I'm going to do is try and generalize this idea of the integral being related to the area under the graph of a velocity of any graph. But really what I'm going to focus on, so it's not going to be as general, is for a velocity versus time graph. So I got this velocity function. Some velocity is a function of time. And so we're going to see how the area is related to it. So, okay, I got a velocity versus time graph, and let's say I wanted to find out what the displacement is between times A and B, right? So I would go, oh, well, that's the area under the graph, and if it was a rectangle or a triangle or even a trapezoid, I got this thing, you know, I can do this. But this is a little more confusing. This is some weird curved shape, so I can't just use some area formula to figure that out. So, okay, what I could do is actually try and break this up into little chunks. I could break this up into a bunch of little rectangles and calculate the area of those rectangles. And when I'm done with that, I'll just sum up those rectangles. That'd be a pretty close approximation to what it was I was doing. Yeah. So, okay. So let's say I did that though, except I broke them up into equal distant chunks, right? So they're not going to be delta x. I'm actually going to call them delta t because it's time down here. The general way, if you did this in calculus, they call those parts delta x because in math, typically, the horizontal is the x direction. But anyway, okay, so I'm trying to find all this little bits of area so I can find the displacement of this velocity versus time graph for this velocity as a function of time. And I'm trying to find the displacement between points A and B, times A and B right there. So, okay, I would get all these little these little chunks, and these are all equal. These are all the times are equal. I'm doing that on purpose. That's kind of the point of this part. And then I go, okay, so this would be the velocity at, I'm just going to arbitrarily call it, this is the velocity evaluated at 1 at that point. This is the velocity evaluated for section 2 right here. So it's the velocity evaluated there. The velocity here evaluated at 3 would be here. The velocity evaluated for the bar 4 up there is at 4. So that's the height of all those things. And then basically to get the area, which is the displacement, right? So the area, which is the displacement area, it's just going to be the time, delta t, multiplied by the velocity evaluated at 1. Plus, for 2, it'd be the time for the velocity evaluated v2. So it'd be delta t, that same base right there, times v2, plus delta t, again that base, and then the velocity is v3. And then lastly, delta t with this velocity, v4. Right? And then now I just got to add all these up. Well, one thing I could do to make the addition a little easier is, hey, that's delta t for each one of them, and the delta t is the same. It's like I did this on purpose, right? So this delta x, which is the area, is just going to be delta t. I'm going to factor out the delta t's, multiplied by, I'm actually going to put the delta t at the end. So it's going to be v1 plus v2 plus v3 plus the velocity evaluated at 4 for rectangle 4. And then that's all evaluated outside of delta t right there. So there you go, and if I added all those up, I get a good idea of what the area is. However, not as accurate, right? Not that accurate. I mean, again, I'm trying to make up for, I got more area here and less area here, so my hope was, oh, hopefully those things will balance out. But that's not exactly the case. For example, I'm making up a lot of area here, but I'm not making up a lot of area over there. So one solution I could do is go, okay, well, I'm just going to split this up into 8 bars then of equal base, and then I'll calculate those up, and I'll get a little more accurate, and that'd be true. Or I could go even more. I'll do 16 bars, or I'll do 32 bars, 64, blah, 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 blah. I don't want to get too far into this. Yeah, I could keep doing that and get more and more and more. So what if I wanted to do, though, let's say I wanted to do an infinite amount of little bar, that I made my delta t so super small that I get exactly the right answer. Well, we basically say when something goes to super small, just like we did to derivatives, if it goes super small, we just say that that's dt. dt, an infinitesimally small amount of time, a super small chunk. And then we evaluate each one of those little bitty chunks at the function vt, right? At some time, we evaluate that function to get that height, and then we add it all up. So we sum all of that up, kind of thing. And then that would be also the area right there. Well, when we do this, when we talk about an infinitesimally small amount of time, and we're adding all that up, it turns out what that actually ends up being is the integral. So the area it's the integral of this velocity as a function of time times some little bit of time. So these are all those little chunks of rectangle right there. That's really what that's saying. Here's the height, here's the base. And then we're going to evaluate that integral between those two intervals. This is what makes it a definite integral. It's going from time A to time B. So there we go. And that ends up being the displacement. So the displacement, which is the area, is the integral from time A to time B of the velocity as a function of time dt. And there we go. That's kind of where we get our main idea. So what we do is we take the integral of that velocity function with respect to time, and once we get that, we evaluate it between the points A and B. Look back at the previous video to see how to evaluate those things, and then you'll get the displacement between those 2 points. So there you go. All right, thank you. Bye.